Alright, welcome back guys. We've got another example here on supernodes. So let's get started. Basically, in this problem we want to find what all of the node voltages are for this entire circuit. So to get started, what we would do is we would draw on a ground, and the ground is it's going to be helpful to draw it in the node that's connecting to the most power sources and most branches. It's often helpful to draw it connected to a voltage source. It's up to you, but I think in this video I'm just going to go with the example that it's down here, just so that we can isolate the voltage source with the method of supernodes, just so you can get an example on how that works. But basically that means that we're going to know this voltage here. This is going to be 0 volts. And then up here on this node, this is going to be, let's call it node A. This one will be called node B, and this node here is going to be called node C. So we have 3 unknown nodes, and we're going to need 3 equations. The first equation that's going to be really easy for us is just doing KCL at node A. And then we're going to need to identify our supernode, and then we'll do KCL at the supernode, and then also do our supernode equation. So in this problem, we're going to want to connect node B and C into one big supernode because they have a voltage source in between them, and that's what we look for when we're doing supernode problems. So let's draw on our supernode here. It basically just includes all of B and all of C. So you don't have to really draw the border around every piece of the node, as long as you get some of them. It should be clear enough. Now we need to identify all of the currents that are going to be flowing into and out of the supernode. So let's just assume some currents here. So let's say we have I1 flowing in, and then I2, let's call this one I2, it's going to flow out. Let's call this one I3 coming in like this, and then I4 basically going out here. And here we know we're going to have basically 3 amps coming in because of this independent current source. So that's everything we're going to need for KCL at the supernode. And then the supernode equation is just the relationship between B and C. So basically C is just 2 volts less than B, or B is 2 volts higher than C. So that will become the supernode equation. But let's get started, I guess, writing the KCL at A expression. So we know we have 2 amps coming in, then we have I1 going out, and we also have I3 going out because there's just one current going through this branch. So we can write that as 2 amps coming in, and then everything going out is just going to be I1 plus I3. And we can really write these in terms of the voltages because according to Ohm's law, V equals IR, we can just rearrange for current and have that current is equal to V over R. So this is the voltage drop across the resistor divided by the resistance itself. So we have 2 amps, and then the expression for I1, well, we're just saying that current is going this way, so it's going from a higher voltage to a lower voltage. So the difference is VA minus VB. That's the voltage drop across the resistor, and we divide it by the resistance of just 1 ohm. And then for I3, that's the current flowing through this resistor. And again, our voltage drop across this is going to be VA minus VC. So, whoops, that shouldn't be an equal sign, that should be a plus. And then we have VA minus VC all over the resistance of that resistor, which is 3 ohms. So we can just multiply everything by 3, and I'm just going to drop some of the units here. So we're just going to have 6 is equal to 3 times VA minus 3 times VB plus VA minus VC. And we can just simplify that a little bit, so we get 6 is equal to 4 VA minus 3 VB minus VC. Okay, so that one's good for now. We can also come down and write KCL at our supernode. So we're going to have all the currents flowing in equal all the currents flowing out. So the currents that come in are I1 plus I3 plus 3 amps over on the right side, and the currents that flow out are I2 and I4. You could move one of these sides over to the other and sum it all to 0. It's the same thing. So we already have expressions for I1 and I3, and then we also just have 3 amps coming in, and then for I2 we just have VB minus 0, so that's going to be VB as our voltage drop over the resistance, which is 3 ohms. And then for I4, again, we just have VC minus 0, so that's VC over the resistance, which is 1 ohm. And then we can just simplify this a little bit, so we get 4VA minus 4VB minus 4VC plus 9 equals 0. And that is our expression for KCL at the supernode. And then the last equation that we need is our supernode equation, which is just the relationship between the two nodes inside the supernode. And that's just saying that VB is equal to VC plus 2, because VB is simply 2 volts higher than VC. So what we can do is we can just take VB here and plug it into our expression for KCL at A. And after we simplify a little bit, we're just going to see that VA is equal to VC plus V3. And then what we want to do is we want to take that and we just want to plug it into VA right here. And then we also want to take VB, which we already have a nice expression for, and plug it in as well to this expression for KCL at the supernode. So we're going to have 4 times VA, which is just VC plus 3, minus 4 times VB, which is VC plus 2. And then also we just still have to subtract minus 4 VC plus 9, and that's all equal to 0. And then what we can do is we can just rearrange this a little bit and simplify, and we're going to find that VC is equal to 13 over 4, or 3.25 volts. And once we have that, we're just going to plug it into our expression for VB, so we can just bring down a copy right here. And when we plug in VC, we're just going to see that VB is just equal to 3.25 plus 2, or in other words, VB is equal to 5.25 volts. And now that we have VB and VC, we just plug them back into the expression for KCL at node A. That works. And maybe let's write that down here. So we have 6 is equal to 4 VA minus 3 times VB, which is times 5.25 volts, minus VC, which is 3.25. So we're going to get 6 is equal to 4 VA minus 19. And then we can just rearrange that. That's 25 over 4 is equal to VA, or otherwise VA is equal to 6.25 volts. So let's drop some boxes around our answers. We had VB, we had VC, and we have VA for the unknown voltages at the beginning of the problem, which was right here. So yeah, generally you just want to use Supernode to solve problems where you can't solve them based on just pure nodal analysis, and you're always going to want to be connecting 2 of the unknown nodes. If they're separated by a voltage source, then you can just connect those with the Supernode and then solve it, basically just finding the equal number of equations to the equal number of unknowns and going from there. So cool guys, thanks for watching, and I'll see you in the next one.